Dear participants, now at the end of this course on industrial fermentation, let me summarize where we are today and reflect on the way forward. Industrial fermentation has enriched our lives with numerous useful and sustainable bioproducts, such as enzymes, vitamins, lipids, sweeteners, savory compounds, and other food ingredients, but also biomaterials, biofuels, antibiotics, therapeutic proteins, ingredients for cosmetics, and many, many more. And similar microbial technologies are deployed in environmental biotechnology to make clean water, soil, and gases. The grand adventure for us now is to come up with more and better bioproducts that can be commercialized faster, cheaper, and with less risks. For major steps forward, we have drafted and published a list of 8 requirements, all with a zero element. The topics range from zero spills of carbon, water, and energy to zero sensitivity for variations in the environment of the cell. You can refer to details in the published opinion paper, but let me here highlight the last and perhaps most powerful of the requirements: zero development time. If we could reduce the development time of a bioprocess to the absolute minimum, this would bring many benefits, such as faster commercialization, lower costs, and no surprises upon scale-up. First, we adopt the philosophy of beginning with the end in mind. Designed from the perspective of the industrial scale fermentation makes clear that we have to accommodate stresses for the microorganisms, both static stresses via product and osmotic inhibition, and dynamic stresses for concentrations of limiting nutrients, pH due to titrant addition, and temperature related to cold and hot spots in the fermenter. These stresses can easily derail the cells and reduce their performance. By investigations, we should try to maximize tolerance of the cells and robustness of the fermentation system. Today, 2 key tools at hand are sensing and simulation. Sensing is the measurement of key process and control variables, and simulation is applying a computer model to calculate the process and control variables. It should be understood that in industrial practice, the measurement data will be scarce due to risks of technical errors and contamination. And also many things cannot be readily measured, such as cell and product concentrations, cell population heterogeneity, and cell lifelines, local limiting substrate and oxygen concentrations, and dissolved gases like carbon monoxide and hydrogen. Also, rates cannot be directly measured. They must be calculated using balances. The computer model can fill this gap, compute the missing measurement data, and reconstruct the local fermenter conditions. Detailed modeling has much advanced in recent years, and we have now powerful high-resolution models to compute gas-liquid flow and hydrodynamics using computational fluid dynamics, metabolic details via metabolically structured models, and population effects using lifeline models. This all can readily visualize the metabolic activity from the perspective of individual microorganisms and make clear how often there are metabolic regime switches and how severe is the stress upon the cell. This approach has also been applied to the industrial fermentation of 1,3-propanediol in the 600 meter cubed bubble column operated by DuPont Tate & Lyle Bioproducts. And for details, I refer to this article by Bisgård and co-workers from 2022. The models can be used to monitor, control, and optimize the industrial fermentation, but an even more important use is for scale down. Statistical analysis of the lifeline data will reveal the cellular environment and gives guidance how to simulate this environment in the lab fermenters, as well as in the screening units, with microtiter plates or microfluidics units operated by robots. From our analysis, we concluded that a single lab fermenter with variable input of feed or mass transfer between gas and liquid and possibly dynamic variations of the pH and temperature resembles closest the industrial conditions. The variations in organic feedstock and dissolved gas concentrations are often a factor 10, with an average cycle time of 30 to 60 seconds. And for the high throughput microfluidics platforms, the ability to make rapid changes in the order of seconds is even better than in lab scale fermenters. At this point, we can now see unfolding the contours of future scale down and scale up of industrial fermentations. The trial and error approaches of today will be more and more replaced by rational, model-guided approaches that are not only better and faster, but also we can envision that traditional intermediate steps such as shake flasks and lab scale and pilot fermentations will become obsolete. And we will be able to directly scale down and up between screening and industrial fermentations. Let me conclude this unit and also this whole course with the following 4 messages. Zero concepts enable fast, environmentally sustainable and low-cost development and commercialization of bioproducts. Conceptual design is essential for success. Dream work precedes teamwork. The process of innovation should begin with the end in mind. Sensing data and high-resolution simulation tools and methods are necessary for fast development, scale down, and commercialization, scale up. What are then the future bioproducts and related bioprocesses? We can distinguish 2 categories. On one hand, we have the top value chemicals, simple molecules, like those advocated by the American Department of Energy. Selecting the right feedstock will result in metabolic energy generation, and the fermentations can be anaerobic, operated at very large scale in a continuous mode with cell retention, with special, often extremophilic microorganisms. And these can be GMOs, genetically modified organisms, and they are tailored and fit for the process at hand. On the other hand, we have the high added value compounds, more complex functional molecules that require metabolic energy input and can be applied as food and feed ingredients or in the pharmaceutical domain. These bioproducts will continue to be manufactured in aerobic fed batch fermenters with mostly non-GMO microbes that have a safe status. The innovation valley of death then will be easier to bridge if you approach it from the end, beginning at the other side of the valley and applying zero thinking to leap to the ultimate performance. And that, dear participants, is the grand adventure of biochemical reaction engineering. Rests nothing but thanks for taking part in this course.